Hello, welcome to The Naked Scientist this week with me, Chris Smith, and also with Priya Crosby. Hello, Priya.
Hello, and this week we find out how to get vaccinated without the need for needles, the buried bog body which has remained perfectly preserved from the Bronze Age, and sleep. Why do we need it? And why do some people fall asleep at the wrong times?
If I'm in a conversation with friends, all at once I might say something that has nothing to do with the conversation, like a little bit of a dream. And then my friend will be like, "What did you just say?" And then I'll be like, "What? Oh, I don't know. What did you say? What did I say?" And that happens once or twice a day.
Sound familiar? Well, perhaps you've got the same condition as that patient who we'll be hearing a bit more from later in the programme. Meanwhile, here's something to get your head around, and hopefully it won't keep you up at night. What we want to know is which mammal spends over 80% of its life asleep. You can find out later in the programme. Meanwhile, if you'd like to get in touch with us, you can tweet at Naked Scientists, or you can email chris@thenakedscientists.com.
The Naked Scientists podcast is powered by ukfast.co.uk.
And let's kick off with a look at what's hot in the science news headlines. Priya.
I found an interesting story this week on the subject of vaccination. Normally when most of us are vaccinated, we think of it as being some kind of shot in the arm with a needle. But it might be a more effective way of vaccinating people if we can put it into the body in a more natural way, for example, breathing in or eating it. And that's exactly what this group at MIT have been doing. However, normally if you breathe something in, like a vaccine, a weakened virus, which is often what's in a vaccine, the body's used to this kind of thing, it sees it a lot, and it would just clear it before the body had any time to produce any kind of immune response to it. So what this group have done at MIT is they've got these lipid nanoparticles, these very small fat globules, and they've put the antigen, the weakened virus, inside it. And then they've looked at what happens if you breathe these across the lungs. And it seems that these aren't cleared so easily and perhaps might be more effective. They compared these nanocapsules with weakened virus inside them to just an antigen or just a normal vaccination in the bloodstream on a group of mice. And they found that those that were vaccinated using just a shot in the arm or just the antigen without this lipid particle to aid delivery, when challenged with the actual virus they were meant to be vaccinated against, it wasn't really effective and they in fact all died. Whereas those mice that had had the vaccination across the lungs with this antigen inside a lipid particle seemed at about 5 days to be pretty much over their infection and were feeling quite good. So it seems that this kind of vaccination using a lipid particle across the lungs might be a really effective avenue for new kinds of vaccination, particularly for viruses that you might normally experience when they're breathed in across the lung.
So you take a virus particle, a weakened one, wrap it up in a sort of oily bag, it gets carried across the airways and presented to the immune system far more efficiently and in far greater amounts than if you just present the virus on its own, and that's what drives this stronger immune response.
Exactly, and particularly because when it's in this nanoparticle, it's actually around in the system for a bit longer because it's a bit bigger and a bit harder to clear. So you're exactly right, it mounts this much stronger immune response.
They've tried that with a virus, you say. Will any virus potentially be amenable to being wrapped up in these oily bags? Or what about other things like bacteria?
I'm not sure about bacteria. Bacteria are quite a lot larger than viruses. It might be that they're a bit too big for this kind of treatment. But I think there are quite a lot of viruses, particularly ones of the lung, that might be really effective for this kind of vaccination.
So things like the flu, potentially?
Well, potentially, indeed.
Thank you, Priya. Well, sticking with microbiology for a minute, one of the things that's surfaced in the media quite a bit in recent months is the issue of antimicrobial resistance, the whole idea that within maybe a decade or so, we're going to run out of drugs that actually work against microbes because they're all becoming resistant. And in fact, this is made more acute by the fact that if you look at the drugs that are in the pipeline that pharmaceutical companies are developing against bacterial infections, there are very few of them. So we really face a problem in the future with no new drugs and the drugs we have got not working anymore. So there's a paper out this week which does give us some hope nonetheless. It's in Science Translational Medicine by two researchers at the Technical University of Denmark. This is Leila Imamovic and Morten Sommer. And what they have hatched out is a plan to use something called collateral sensitivity, because what they've realised is that if you give bacteria one drug to kill them, as those bacteria become resistant to that drug, very often it forces them to drop their microbial guard against other kinds of antimicrobials. In other words, you can find bacteria becoming very, very supersensitized to other types of antibiotic other than the one that they're becoming resistant to. So they do this really nice series of experiments where they take E. coli, which is actually causing quite a few infections in hospitals these days, and they make these E. coli resistant to 23 different antibiotics. So you grow each of the strains of bacteria in a low concentration of the antibiotic until it becomes resistant to that antibiotic. And then they test each of the 23 which are resistant against their own antibiotic against all the other 22 antibiotics to see which ones they've become more or less sensitive to. And they find that 17 of the 23 that they test out show this collateral sensitivity, becoming up to 8 times more sensitive to some of the other antibiotics in order to become resistant to the first antibiotic. And so what they've now been able to do is to work out a sequence of antibiotics which, if you give, say, drug A and then switch to drug B, then what will happen is that anything that's become resistant to drug A will now be super sensitive to drug B, and that will wipe them out, and it will kill the other ones anyway. And they've managed to come up with up to 200 cycles of different drugs, either using 2, 3 or 4 antibiotics in succession, which should prevent resistance developing in certainly E. coli and other what we call gram-negative bacteria like it. And when they tested it against 2 clinical strains of E. coli, which were resistant to 8 different antibiotics, they found that their strategy worked absolutely perfectly.
So are you saying that we'd just give these drugs in a cycle regardless of what the bacteria was like in the first place? Or would you test the bacteria first to see what it might be resistant to and then apply an appropriate cycle of drugs to that?
That's right. So you've got to start with a drug to which the bacteria are sensitive, and that will involve some testing. But then what you would do is, rather than just switch to any old antibiotic if they become resistant, you use one of these specific cycles they've developed so that the bacteria which are becoming resistant get killed off by the second drug you give, and then any that become resistant to that you kill off with the third drug you give, and you give this quick cycle. And rationalised across a range of different antibiotics and different types of infections, you could have a really powerful tool here to prevent infections like this becoming entrenched in hospitals. So it's very encouraging.
So it's like a treatment that's personalised for the bacteria.
It certainly is. Priya, thanks very much. Now, a 4,000-year-old Cashel man who was unearthed in Ireland has now been crowned as the oldest so-called bog body with intact skin anywhere in the world. But why do wetlands and peat bogs preserve people so well? Here's Kate Lamble and Matt Burnett with the Quickfire Science.
A bog is an area of wetland covered with sphagnum moss and peat or partially decayed vegetation.
Hundreds of bodies preserved in these areas have been uncovered across Europe. Several have been found in Ireland, including the Cashel Man in County Laois.
If a body is buried in a bog soon after death, the lack of oxygen, low temperatures and high acidity of the environment mean that bacteria can't begin to decompose the body. This preserves internal organs, clothes and even hair.
However, over time, bodies are often crushed under the weight of the peat. The acidic conditions also dissolve the calcium in the deceased's bones, making them either floppy or completely vanish.
Not all bogs preserve bodies equally well. Lower levels of acidity and higher water flow can turn some remains into skeletons rather than mummies.
Once removed from the bog, the Cashel Man needs to be sprayed with deionised water to prevent him from decaying at room temperatures. In the long term, bodies are preserved by soaking them in a water-soluble polymer and then freeze-drying the remains.
Radiocarbon dating suggests that the Cashel Man is around 4,000 years old, dating from the early Bronze Age. This is earlier than most bog bodies, which date from the Iron Age.
However, we don't know how closely he is related to the current Irish population, as the preservation process also destroys DNA material.
Bodies are typically uncovered by those digging for peat to use as fuel. The first recorded discovery of a bog body was in the 17th century, and for the next 200 years, bodies were typically buried in graveyards, as it was presumed they were modern victims.
A high number of bog bodies have been found to have died of violent wounds, leading archaeologists to speculate that some may have been sacrifices. The Cashel Man's spine was broken several times, and there was evidence of a sword or axe cut on his arm.
Matt Burnett and Kate Lamble. And you can get hold of all our Quickfire Science episodes as their own podcasts from our website at nakedscientists.com/Quickfire Science.
You're listening to The Naked Scientists with Chris Smith and with Priya Crosby. In a minute, we're going to be talking about sleep why it eludes some people and why other people find they struggle to stay awake. If you would like to ask us any questions about sleep, you can tweet at Naked Scientists, or you can email chris@thenakedscientists.com. Scientists have known for a little while that probably all living things, us included, have a 24-hour body clock ticking away inside them that keeps track of time, so they know when to wake up and when to go to sleep. But this week, researchers at the universities of Aberystwyth, Leicester and Cambridge have discovered a marine animal that also has a tidal clock. As well as the time of day, it can tell when high tide is due. David Wilcoxon is the senior author on this paper in Current Biology. He's with us now. Hello, David.
Hello, Chris.
So what is this creature?
It's a small crustacean, lives on sandy shores around the UK, and it's called Eurydice pulchra. It's the speckled sea louse. It's only about 5 millimetres long, and it's a marine relative of the woodlouse.
Why does it need to know when the high tide is coming?
This animal lives buried in the sand when the tide is out. When the tide comes in, it comes out of the sand to swim. And so it needs to know, anticipate the tide so that it can gear itself up to swim for 2 or 3 hours and then bury back into the sand before the tide goes out. And so it doesn't get stranded at an inappropriate point on the shore. It stays in its preferred position.
So how did you discover that this organism has this tidal clock?
Well, we've known this for quite some time. In fact, one of the authors on the paper, Mick Hastings, did his PhD on Eurydice way back in the 80s. And we know that it has rhythmic behaviour, swimming rhythm, with a 12.4 hour or a tidal period. But what we didn't know is how this 12.4 hour activity was governed, whether it was simply a 24-hour clock that was running at a different speed, or whether it's a unique tidal oscillator, or a tidal clock. And this is what we've been working on to really uncover how these 12.4-hour rhythms are driven.
How have you done that?
So we've used modern molecular biology as well as quite elaborate behavioural experiments where we manipulate the light regime the animal's exposed to. So what we've done, we've sequenced lots of the genes that we know are involved in daily rhythms in other organisms. We've sequenced those from Eurydice. And one of the things we've done is we've knocked down the expression of one of these genes, and that has disrupted daily colour changes in the animal, but actually left the 12.4-hour swimming rhythm intact. So we've removed the daily clock, but left intact the tidal clock.
I see. So what you're doing is you're saying there are some things that this animal does every day according to the time of day, and that's driven by its normal body clock. And if you dismantle the body clock using various tricks, which you've done, then those daily things go away, but it still has this swimming activity every 12 hours, showing it's keeping track of tides in a separate way to the way it keeps track of normal time of day.
That's exactly right. So what I should have said is that as well as having a 12.4-hour swimming activity, the animal also changes from dark to light on a daily basis with the light-dark changes of night and day. And also when it's having a high tide at night time, it swims more than it does during a high tide at daytime. So it's a daily modulation of the tidal swimming. And we can actually, as you just said, reduce those by knocking out the daily clock, but we cannot change the 12.4-hour rhythm of swimming. So we've disentangled or disassociated these two clocks.
The fact that it's got two different clocks running in its brain, do you think that's unique to this creature, or are there many other creatures, perhaps even humans included, that have other clocks other than our daily body clock?
Well, that's a really important question. In fact, the answer to that is definitely not unique to Eurydice. This is our model organism for non-circadian rhythms, for tidal rhythms. But we know that there's many other marine organisms that also have 12.4-hour rhythms of activity, and also lunar rhythms and semi-lunar rhythms of reproduction, for example. There's a paper published at the same time as ours on a small marine worm that has lunar rhythms of reproductive cycles. And they've shown also that they can disentangle a circadian or a daily clock and their lunar clock. So they've come up with similar results but in a different organism.
But you don't yet know what this clock is or how it runs.
Well, that's the big question really is what's the nature of this clock and how is it orchestrated, how this 12.4-hour rhythm orchestrated at the molecular and cellular level, and that's something that we're getting close to having an answer on, and we're working on very hard at the moment.
All right, we must leave it there. David Wilcoxon from the University of Aberystwyth, thank you very much. Priya.
Now, another story that caught my eye this week was on the subject of Parkinson's. Parkinson's is a motor disorder that's reasonably common. And what happens in Parkinson's is that you lose a number of cells of neurons in the brain that produce a particular type of chemical called dopamine. And when you lose these cells is when you start to see these movement problems. And so ideally we'd like to see some kind of cure for this. And that's exactly what's been going on with this group run by Jan Takahashi at the University of Kyoto. So what this group has done is they've taken monkeys. They've taken a normal cell from the monkey's mouth or from their blood. They've turned back the clock on this cell and persuaded it to become a stem cell, a cell that's able to differentiate to decide to be lots of different types of cells. And then they've persuaded them to become some kind of dopaminergic neuron, these dopamine neurons that are lacking in the brains of people with Parkinson's. Having done this and created these cells from these monkeys, what they've then done is injected the cells back into their brains, either into the monkey from which the cell was originally derived, or into a completely different monkey. And they pretty much just left the monkeys alone for about 3.5 to 4 months. They didn't give them any kind of immune system suppressing drugs or anything like that. They just put the cells back into the brain and left them alone. After 3.5 to 4 months, they had a look to see how these cells were doing in the brain. And the results were reasonably surprising. They found that both types of cells, whether they came from the monkey in which they were now present, or they came from a completely different monkey, there had been some kind of immune response. There'd been a bit of inflammation and things, but they were still seen to be there in the brain, and they seemed to be living and kind of doing all right. And this is quite surprising, because normally in any other part of the body, if you were to take a cell from a completely different person or a completely different monkey and put it into a different monkey or person, you'd have a huge immune response. But it seems that in the brain, it didn't really differentiate that much between cells that came from a monkey itself or from a completely different monkey.
So what do you think the implications of this are, Priya?
So this is particularly interesting because it means that we can make dopaminergic neurons and put them back into the brain. And this has got a real potential for the treatment in Parkinson's. Perhaps we can replace these neurons using these stem cell-derived dopaminergic neurons. What's particularly interesting here is it doesn't seem to matter that much where the cells come from. They don't have to be derived from the person's own cells. So the potential here is that we have a very generic treatment for Parkinson's. We could just pretty much grow a standard set of dopaminergic neurons and inject them into the brains of people with Parkinson's. Now, we're not quite sure how well these cells function in terms of actually solving the motor problem, but it certainly is a really interesting avenue for treatment in Parkinson's in the future.
Certainly very encouraging. Thank you, Priya. Now, you might have caught the news stories this week showing an individual in China who had a new nose apparently growing on his forehead. And so the story goes, because the details are slightly sketchy, this individual had sometime last year been involved in a car accident, and that had led to an injury to his face, and he then succumbed to an infection in the skin and soft tissues of his nose, and this infection destroyed the cartilage of his nose and led to his nose collapsing and profound disfigurement. And doctors in China, in the Fujian province where he lives, have resorted to a fairly radical and clever way to repair this. And we thought we would invite in Mr. Nakul Patel, FRCS, who's a plastic surgeon, to tell us a little bit about this technique. Why would they have grown the nose on his forehead, and what's the sort of plastic surgical intervention that's going on here, Nakul?
Sure. So they've used the forehead as a flap, as a block of tissue that's moved down to reconstruct the nose. But prior to that, they've actually used the cartilage from the patient's own ribs to reconstruct the framework that will form the shape of the nose. And then thereafter, as a subsequent procedure, they'll transfer this to recreate the nose.
So why not just put the cartilage straight onto the face and borrow some skin from somewhere else and build the nose in situ? Why go through this rigmarole of growing a nose up there?
It's quite a novel way of doing things. The standard way would be exactly as you've described, and they've just tried to differentiate. And I think the media has caught the wrong end of the stick in some parts. They've suggested that this new nose has been grown, whereas actually it's not necessarily that it's been grown. However, it's just that it's been shaped and placed into the forehead prior to the next operation, which is going to be to move it into its correct place.
How will they do that?
So they take a strip of the forehead tissue all the way up to the hairline. This technique's well established. It was sort of described as early as 700 BC. and then they place it onto the nose. They leave it attached for a period of about 3 weeks, by which time it has sufficient blood growth from the edges such that tissue is likely to survive. And
Oh, I
then
see.
they
When you say
divide-
leave it attached, you mean leave it attached so there's sort of on a stalk from the forehead, and you trim it out and rotate it down, and that way it takes its blood supply with it.
That's exactly correct. And once it's got its new blood supply from its new home on the nose, they're then able to divide the stalk and place the remainder of the stalk back onto the forehead.
Why use forehead skin to do that? I mean, apart from the fact there's a blood supply there, is there any benefit of using that part of the body as opposed to any other?
It's a very good question. The forehead skin is a really good match to the rest of the skin of the nose, and that's why this procedure that's been done such a long time ago, it stood the test of time. So, yeah, we continue to use it to this day.
Is this likely to be successful for him?
Looking at the pictures in the media, I think he's got a good reconstruction with regards to the shape of the nose, and I'd hope that if all of that survives, he'll have a nice reconstruction.
What problems could he succumb to when they try to do the final movement?
The worry would be if any of that cartilage doesn't have a sufficiently good enough blood supply, if any of that gets resorbed, in which case it will lose its shape. If there's any infection, again, the same problem could occur.
And what about closing up the forehead where the nose is at the moment? How will they close the skin together so that you don't leave a gaping nose-sized and shaped hole on the man's forehead?
So most of the lower part of our forehead up close to our eyebrow can be closed directly, so that will leave a straight line scar. You might well leave a small area on the forehead, which is quite high up, to heal on its own, or place a small skin graft on that.
Nakul, thank you very much. That's Nakul Patel. He's a plastic surgeon from Addenbrooke's Hospital, joining us to talk about the case of the gentleman in China this week who has a new nose growing on his forehead to replace one unfortunately lost in a car accident.
And as always, you can find more information, including the references for all the papers we discussed, on our website at thenakedscientist.com/news.
You're listening to The Naked Scientists with Chris Smith and with Priya Crosby. Our main topic for this week is sleep. We spend a third of our lives doing it, and in fact some animals spend over 80% of their lives asleep. And we asked you at the beginning of the programme in our quiz for this week, can you tell us which animal does that? Andrew in Huntingdon is speculating by email, chris@thenakedscientist.com, that it's the dormouse. I can tell you, Andrew, it's a good guess, but it's not the right one. Priya.
But what's the purpose of sleep? Why do we need it? And why does it become a problem for some people? Tim Cornell is a consultant at the Sleep Centre at Papworth Hospital.
Sleep is about a transition from when we're fully alert and interacting with our immediate environment. When we go to sleep, consciousness gradually drops. There are several levels of sleep and types of sleep, so very light sleep isn't always perceived by someone. But fairly rapidly, at the beginning of the night, we'll go into quite deep non-dreaming sleep, and it's called slow wave sleep because the brain waves slow down. And that's, if you like, the big money sleep that fills up the sleep bank, pays back the debt of wakefulness, because one of the chief drives to sleep is how long you've been awake beforehand. So we'll go into deep non-REM sleep, and then after a cycle of sleep lasting about an hour, our sleep will lighten and we'll go into dream sleep, and that's called rapid eye movement sleep, or REM sleep. So that's a different type of sleep, and in fact, when they've looked at brains with special imaging during dream sleep, the brain is as active as wakefulness, but we are nonetheless asleep. And then once we've had some dreaming, we'll go back to non-REM sleep again, and the cycles continue through the night. As the night proceeds, there is less deep sleep because the sleep bank is being filled up, if you like, the debt is being paid off, and there is more dream sleep.
Roughly how long is any one of these cycles? Went a cycle of non-REM and then REM sleep?
It's about an hour and a half, 2 hours, but it varies greatly through the night and between individuals.
And so we've got a concept of what normal sleep looks like. How do we define a sleep disorder? I mean, a lot of us will have a night or a few nights when we struggle to sleep, but when does that, what I would call normal inability to sleep, become a disorder?
All of us can have a bad night now and again. Perhaps if we've got something big happening the next day, we might not sleep so well. If it becomes more deeply entrenched than that, so perhaps if there's a reason to not sleep well one night, but then that reason has happened the next day, but our sleep problem persists, that might be starting to become a disorder. It's when it becomes over several weeks or months. And that's really what I'm talking about there, is typically insomnia, which is commonly experienced where people can't sleep very well at night. But there are other disorders which typically gradually develop, and they are specific disorders of breathing or where the brain's control of sleep and wake becomes dysfunctional.
So you mentioned insomnia. Do we know exactly what happens when someone has insomnia? We all have an impression that they struggle to sleep, but do we know what's going on at a sort of more neurological level?
There's not a lot known about why people have insomnia. There's some evidence that people with insomnia seem to be hyper-aroused. When you look at their brainwaves during sleep, they seem to not be having such a deep, solid sleep, but there's no clear understanding as to why. There are some other sleep disorders which present as insomnia. For example, there's a condition called restless leg syndrome where legs are fidgety, particularly late in the night when people are tired and finally lying down to go to sleep, and the legs become uncomfortable and there's an urge to move them, and that can disrupt sleep and cause insomnia. And then there are other disorders of breathing where we stop and start breathing without necessarily knowing about it, but what the patient can be aware of is of poor sleep because they're constantly interrupted by the breathing pauses.
You mentioned there problems with breathing disorders. Is that just a disruption of sleep? What exactly happens there?
Sure, so obstructive sleep apnea is what I'm talking about, and that's probably the commonest breathing disorder during sleep, aside from insomnia. And what happens with obstructive sleep apnea is that the throat relaxes and closes or becomes very narrow so that breathing becomes obstructed. And so, if you like, the person suffering from obstructive sleep apnea is choking themselves awake repeatedly during the night. Usually they only wake up for a few seconds, so they don't remember it, but what that means is that their sleep is peppered by brief awakenings. And so typically what happens, if it's frequent enough, is that they wake up unrefreshed by their sleep and they're sleepy during the day.
What can we do if someone has obstructive sleep apnea?
People can have suggested symptoms, and we have to take them forward for tests to confirm the diagnosis. And then we look at how bad their symptoms are and how much apnea is occurring, how many times they're stopping breathing overnight. It may be that simple lifestyle measures would improve the situation. So mild sleep apnea may respond to weight loss because that's a major risk factor for the development of sleep apnea. Sometimes it only happens when someone's lying on their back, so we can talk about measures to avoid sleeping on their back, and that can do the trick. Sometimes if sleep apnea is more severe, then they need specific treatments. And one way of treating it is to wear a mask called CPAP, which stands for Continuous Positive Airway Pressure. And this is a mask connected to an air pump which blows air through the throat to provide a pneumatic splint to the airway to stop it from flopping shut.
If someone thinks that they might have insomnia, what options are there out there to treat or manage the condition?
Well, many bouts of insomnia settle spontaneously, so it'll be short-lived and it may well relate to something that's going on in someone's life. But if it becomes protracted, it's about taking a step back and looking at what things you might be doing but aren't helping the situation. Has someone got into the bad habit of working very late and then switching their light straight out, having caffeine in the evening, all that sort of stuff? It's looking at the sleep environment. Is it appropriate? Is it quiet, dark, comfortable, that sort of thing? And also, what does happen with insomnia is it tends to feed on itself. So even if the initial stressor that's triggered the insomnia has been dealt with and resolved, the concern and the anxiety about not being able to sleep tends to feed it. The worst thing that can happen for insomnia is to be worried about sleeping, because if we do that, then it gets worse. And that really is something that probably most of your listeners will recognise. If they are having a night where they're thinking about something important the next day, they're worrying about that, then they realise they're not sleeping, and they start worrying about that, and sleep becomes even more elusive.
Thanks to Tim Cornell from the Sleep Centre at Papworth Hospital. So the best thing for insomnia is actually to stop worrying about it. Easier said than done in my own experience. I find that if you struggle to sleep, you end up just getting into a loop and you get more and more worried about it, and it stops you sleeping altogether.
What did you think stopped you sleeping?
Worrying about not sleeping.
But what do you think got it going in the first place?
I think I had to get up early for a few things. Then you start thinking, oh, I'm going to have 5 hours, or am I going to get 4? It just rolls in itself pretty much.
I know what you mean, though, because when I've been in situations where you worry because you've got a big day ahead, and then you worry because you're not sleeping because you've got a big day ahead, and you're worried about being lethargic and tired the next day, and then actually worrying about not getting enough sleep takes over, doesn't it?
Exactly.
You're listening to The Naked Scientists with Chris Smith and with Priya Crosby. And if you'd like to follow up on the programme online, nakedscientists.com is the web address. If you'd like to get in touch with any comments or questions, or to answer our quiz question this week, which is which mammal spends more than 80% of its life asleep? And we've also heard from Joe in Peterborough, who says, is it a sloth? No, it's not a sloth. Sorry. please let us know. You can tweet at Naked Scientists, or you can email chris@thenakedscientists.com.
So far, we've touched on the problem of insomnia, where people can't get to sleep. But a more serious sleep disorder is narcolepsy. Sufferers regularly fall asleep during their daily lives because they can't regulate their sleep patterns properly. Julie Flygare writes a blog about what it's like to have the condition.
For me, the first thing was when I was laughing about a joke, my knees just slightly buckled. It was like the strangest feeling, like almost like I melted inside. But then my friend said she didn't see anything. So I thought, okay, I don't know what that was. And that weakness became worse and worse over a few years. Always when I was laughing at jokes or if I was annoyed, then my body would start giving out on me. And I asked a lot of doctors about that. And around the same time, I was also in law school. And I just started law school, and I was having such a hard time staying awake through all my classes. Some of my notes from class would have words from dreams, like mixed in with the lecture, and like celebrity names, and then half sentences. So I was conscious, but not really actively engaged in my classes. So I really didn't think of it as a sleep disorder for a long time. I just thought it was like my personal problem. And it wasn't until one morning that I was trying to drive to school after getting like a full night's sleep. I got to school, and I woke up in the parking lot, and I didn't remember having arrived there. So that's when I thought maybe I have a sleep disorder. So I went to a few different doctors, and it took a while, but eventually found narcolepsy with cataplexy as my diagnosis. Once I was diagnosed, I thought I would take medication and go back to my life the way it was before. So I take medication twice a night to help me get into a better form of sleep, because we spend too much time in REM, dream sleep, and we're not getting stage 3 restorative sleep. And then I take daytime stimulants during the day. But even with all that, I still nap twice a day, and that's really unpredictable. I feel pretty energetic, and then slowly I lose my ability to really concentrate and think straight and make good decisions. And if I'm in a conversation with friends, all at once I might say something that has nothing to do with the conversation. It's almost like I've almost entered like a little bit of a dream. And then my friend will be like, "What did you just say?" And then I'll be like, "What? Oh, I don't know. What did you say? What did I say?" So I just kind of fizzle out, and that happens once or twice a day. So as soon as I start feeling that way, I try to take a nap. I still have that cataplexy where my body gives out. It's not nearly as bad as before I received treatment. If I hadn't started treatment, I would have had to been in a wheelchair. It got so bad that I was completely collapsing to the ground, paralyzed for a minute or two. And there's another symptom, these hypnagogic hallucinations. So when I wake up from a nap or sometimes during the night, I really think things are happening to me, that someone's come into my apartment and maybe it's a burglar or someone's going to attack me. And I really feel like I can see them and hear them and feel touch, but they're not really there. And that still happens to me quite often. And that's also because the boundaries between this dream sleep and consciousness are kind of broken. So aspects of dream sleep are happening when I'm too conscious.
Julie Flygare, who writes the blog julieflygare.com, describing her experience of narcolepsy.
How can we probe, though, what is going on in the brains of people who have sleep disorders, like the one Julie was describing? Jason Reel is from University College London, where he's actually using zebrafish to learn more about sleep. Hello, Jason.
Hello.
How on earth do you understand sleep from watching fish?
The first thing we can do is very simply watch a fish with a video camera. And in fact, we can watch thousands of fish at once. And then what we can do is we can manipulate them genetically, or we can add drugs into the water and ask, how does their sleep patterns change? And then from there, we can try to understand what's happening.
Are fish a good representation of the patterns of sleep and the systems in the brain that control sleep in even more complicated animals, including us?
Yes. So this concept of non-mammalian sleep is a relatively new one. It's only been about the last 12 or 15 years when scientists have reached a consensus that most organisms, including fruit flies and fish, have a sleep-like state. And in the fish, in particular, not only do drugs that regulate or manipulate sleep in humans also give the same effect in the fish, but also many of the neurons, including those neurons that are lost during narcolepsy, also are present in the fish and seem to have many of the same kinds of neuronal connections that are present in mammalian brains, and also some of the same functional consequences that we see in mammalian brains as well.
So you can do many, many parallel experiments watching these fish, and you can put chemicals into the environment the fish are in to see if they change their sleep behaviour. Have you discovered anything that can manipulate sleep?
In fact, one of the things that we did was we can do a screen, because we can do so many at once, we can do a screen of thousands of small molecules. In fact, we did a screen for several thousand small molecules, and we identified hundreds of different compounds that regulate sleep, either upregulating or downregulating various parts of their behavioral experience. The other thing I should say is that the larval zebrafish are also optically transparent. So another thing that we can do is we can use calcium indicators, which will respond to when neurons are active, and we can actually watch the fish brain while they're sleeping or while they're awake and ask what neurons are doing during different behaviors.
How old are these fish? Because we know that if you study a human, a baby spends the majority of its life asleep, whereas an elderly person spends half the night awake because they can't drop off. So are your fish therefore a good model for a human in that regard?
One thing to realize is that when we talk about larval zebrafish, the comparison to mammalian models is a little bit overly simplistic. So one problem, for example, is that the larval fish, so they go from one cell to a fully patterned animal in about 24 hours. And then at 4 or 5 days post-fertilization, they can actually do complex behaviors, including they can learn, they can hunt. So in some ways, they're more on their own very early on. So they're not necessarily like a human baby per se. They're more like, I don't know, an adolescent maybe.
We heard just before you from Julie Flygare, and she's been describing her experiences of the condition narcolepsy. What can your fish reveal about why she's having those symptoms?
Narcolepsy is a syndrome that is accompanied by loss of these very specific neurons deep in the hypothalamus of our brains that produce a peptide called hypocretin or orexin. And that peptide gets secreted, and through mechanisms that are very complex and somewhat not well understood yet, seems to promote arousal. One of the things that we've done in the zebrafish is be able to manipulate the orexin hypocretin system. We can make mutations that eliminate that function, or we can kill those neurons just like in the human patients. And then, this is one of the things that we're doing right now actively, we can then test, say, some of the drugs that we identified from our previous screen and ask, now these fish that have no hypocretin signaling, how do they respond to these drugs?
And have you got any leads? Do you think you're going to be able to come up with some compounds that will help people with narcolepsy better than the present agents, which all have many side effects that they're currently forced to take?
Well, it's very early days, so I'm reluctant to say too much, but I think we're hopeful that we could screen a large enough compound set that maybe we will be able to find something.
And Jason, we were talking about sleep in baby animals and larval zebrafish earlier, and we got a question in from one of our listeners, David Stovell, and he's asking about sleep in the fetus in the womb. And he says, when a fetus is developing in the womb, does it wake up for the first time, or does it go to sleep for the first time? I think what he's asking here is, when do we start to see sleep and wake cycles in a baby human?
So I know from studies in rodents that you can, in fact, by measuring brain activity, identify what appears to be a sleep-like state during late fetal development. I don't know exactly when in humans that kicks on, but certainly in other species you can identify a sleep-like state during development.
Jason, thank you very much. Jason Reel from University College London. He's staying with us, so if you have any questions for him about the process of sleep and the condition narcolepsy, you can tweet at Naked Scientists, or you can email chris@thenakedscientists.com. Another reason to get in touch is to have a go at our quiz for this week. We're asking you which mammal spends more than 80% of its life asleep. And so far we've struck from the list dormice and we've struck sloths, and a couple of people might be on the right lines. Priya.
So far, we've heard a lot about sleep disorders, but most of us only have our sleep disturbed when we get jet lagged or start working shifts at really odd hours. To find out how this affects us, we're joined by Mick Hastings from the MRC Laboratory of Molecular Biology in Cambridge, who works on understanding our body clocks or circadian rhythms. Hi, Mick.
Hello.
So, we all get tired if we're suddenly asked to do a night shift, but people who do it regularly seem to adapt to these strange alternate hours. Can you tell us, how do our bodies accept this new kind of timing?
Well, you mentioned it yourself in the introduction that we have a clock in our body. In fact, we have probably innumerable clocks in our body. There's a principal clock in the hypothalamus, something that Jason mentioned earlier, which is called the suprachiasmatic nucleus. And that is basically the conductor to a whole orchestra of other clocks spread right across the body. So there are clocks in the liver, there are clocks in the stomach, the immune system, you name it. It's all rhythmic. And nature programmed us to operate on a normal 24-hour day. And that 24-hour day, because the suprachiasmatic nuclei are connected to the retina of the eye, they know, as it were, when it's day and when it's night, and then they can relay that information to all the other body clocks right across our body. Of course, the problem arises is that nature never intended us to jump on aeroplanes and travel across time zones. So that when we do that, in fact, the capacity of our body clock system to adjust to a change in the light-dark cycle is very limited. And at the time we're trying to catch up with the change in the light-dark cycle, this beautiful program that normally controls our physiology and behavior is completely scrambled. And that's why we feel lousy and we're confused and we can't concentrate.
How long does it take our body, roughly, to adapt to this new cycle?
Yeah, so the rule of thumb, and you can demonstrate this in people, you can also demonstrate it in experimental animals. The rule of thumb is that for every hour difference in time zone, it takes about 1 day to readjust. So, you know, when the clocks go forward or back in spring and autumn, that's a 1 hour difference, so it's not too much of a problem for people. But of course, if I were to fly from here to New York, that's a 5 hour time zone difference, and it'd probably take about 5 days for me to adjust to New York time. And then when I come back, I've got another 5 days of readjustment to Cambridge time.
So it's quite a long time to shift between these two cycles. Are there any problems, perhaps not so much with jet lag, which is quite rare, but if someone shifts a lot, for example, if they're doing shift work and they're changing between working days and nights, are there any problems with doing that kind of thing?
Absolutely. I'm sure many of your listeners have worked shifts or have experience of it. It's not a pleasant thing to do from the point of view of the body clock. We can have animals, for example, and change their light-dark schedules and mimic the effects of shift work. And if, for example, you have, let's say, a mouse, which is a type of mouse which has got problems with its heart, if you then mimic shift work changes on the light-dark cycle, that will aggravate the cardiovascular disease that we see experimentally. You can then jump from those experimental observations to look at people. And if you do epidemiological studies, so you look across a large number of people, trying to correct for all the different potential confounding factors, one finds that people who've had a working life on rotating shift work, so they're forever trying to jump from one clock zone to another, then something like they've got a, let's say, 20% increased chance of getting certain forms of cancer or indeed cardiovascular disease. So there is a real life cost for people trying to, as it were, work against their natural body rhythm.
And we've got a question in from one of our listeners here, from Anthony Gortastic, who says that he's a shift worker. He does every 21 days, he does 7 nights. And he wants to know, what's the best thing to do eating-wise? Should he eat meals through the night as if it were the day, or should he just have lots of light snacks?
I mentioned there's a clock in the liver, and that controls when the liver produces the various digestive enzymes. The clock in the liver is actually responsive to meal times. So it's in an experimental animal, if you change the time when they can eat, you see that their rest activity, their sleep-wake cycle stays the same, but the clock in the liver gets pushed out of sync with it. So meal times are a very potent stimulus for this internal synchronization. In terms of what your listener says, given that he's spending most of his time, if it's 7 days out of 21, then he's got 14 days out of 21 on normal schedules. So I think the best thing, my personal view, would be it's better for him when he's on the shift to stick to the meal times he has when he's not on the shift, to stick to his normal routine, rather than try and change things for 7 days and then have to change them back again after 7 days.
Thank you, Mick Hastings from the MRC Laboratory of Molecular Biology in Cambridge.
You're listening to The Naked Scientists with Chris Smith and with Priya Crosby. We're talking this week about the role of sleep and the body clock, and our guest experts, Jason Reel is with us from University College London, and Mick Hastings works at the Cambridge MRC Laboratory of Molecular Biology. Both are experts on the process of sleep and how the body keeps time. For both of you, we have quite a wealth of questions, so let's kick off first of all with this one. Wayne Holmes asks, what are the long-term consequences of too little sleep, especially in children, and is there any benefit, Mick, of having power naps?
Two separate questions. The purpose of sleep, aside from withdrawing from the world and rebuilding your body and repairing damage and taking time out, as it were, the principal purpose of sleep is for the consolidation of memories. So when you sleep, you encode the information which you've taken on during the day. And obviously for children, nothing can be more important for developing brain than to correctly process all the new experiences that children have as they grow up. So short sleep times in children is potentially going to have consequences for their cognitive abilities and probably mood as well. And I think most parents recognise that.
So we've got a question from Elizabeth Worley, and she asks, why do some people talk in their sleep while others do not? Is it the subconscious way of saying things that we don't want to say when we're awake? If you've got any ideas on that.
So I am a sleep talker, but no one in my family over 30-some years of talking in my sleep have ever found me to say anything coherent whatsoever. So I'm not certain if it's a subconscious way of trying to answer or say things that we otherwise wouldn't. It may just be just like when our eyes start rotating during dreams through REM sleep, rapid eye movement. Perhaps when we're talking, it's also just kind of an automatic response like that.
Okay, and we've got another one from Thokazani on Twitter, who asks, I used to dream, but I'm not sure if I still do, or just cannot remember in the morning. Is it possible not to dream at all for months?
Yes. In fact, it's possible not to dream for, as far as we're aware, years. So some patients that take certain kinds of antidepressants and antipsychotics actually have a massive suppression of REM sleep, which is the dreaming sleep. And they seem to have no obvious cognitive impairments due to the lack of REM sleep, which comes to the question, what is REM sleep for? And what are dreams for? And we don't really know. But one idea is that it's a way to prepare the brain for wakefulness. The brain becomes active again after being in this strange slow wave sleep phase, and then perhaps it's just a way to prepare the brain to be active.
I know Chris had a question that's on this topic as well.
I was just wondering, when I dream, I obviously have experiences. And we heard from Mick earlier saying that sleep is all about consolidating memories. So why are dreams so often forgotten? Why are they so hard to remember? And how do I know that they were dreams, they weren't reality?
Yes, this is a very interesting question. So one thing to keep in mind is that even though sleep seems to be important for consolidation of memories, it's not necessarily tied to the dreaming stage of sleep. In fact, many of the studies the clearest studies that link memory to sleep actually point it to being particularly important during the non-REM sleep phase. So it's not necessarily true that the dreams are the part that are the memory replay and consolidation. Now, why you often forget your dream, I think that's probably an adaptation for exactly what you said. How do we know that a dream isn't reality? If we remembered our dreams too thoroughly, perhaps we would begin to become confused about what is reality and what was a waking experience.
Okay, and another completely different question is from Jill Clark, and she says, there's an old wives' tale that says a glass of cold milk will help you sleep. This is actually true. Does digestion of some things make you sleepy?
So my experience is it's been always a glass of warm milk that makes me sleepier. But yes, there are definitely foods that can make us less tired or more awake. In fact, many people have experienced, for example, after a large meal in particular, sleepiness. That's actually a period of sleep called postprandial sleep, which is after eating sleep. And if you look throughout the animal kingdom, think of the mighty lion, for example, feasting on a zebra carcass and then just going off for a big long nap.
Sort of allied to that, Jason, David Bailey says, why is coffee so good at giving you a wonderful boost? Certainly works on me.
Yes, so that is because of what's in coffee, which is caffeine. And caffeine is an adenosine receptor antagonist. So in order to understand how this works, one concept for the timer of what maintains wakefulness is thought to be, in fact, adenosine, which is a small molecule that gets progressively secreted in the brain and builds up during wakefulness. And in certain areas of the brain, it's thought that adenosine is triggering, hey, it's time to go to sleep now. And caffeine is thought to directly interfere with that signal that it's time to go to sleep and give, in fact, a boost to wakefulness.
Okay, and a question that's probably quite appropriate for me as a recently ex-student. From Susan Bayi Howard, why can it be so hard to stay awake in class?
That's a very good question. I think it's a combination of sleep deprivation, so you're not sleeping perhaps enough, and then during a lecture, you're getting a period of quiet restfulness, maybe the lights go down, and those are all being triggers to say, hey, maybe you should go to sleep now. You didn't get enough sleep last night.
And Mick, Karen Marshall says, why do I always wake up 4 hours after I go to sleep, no matter how tired I am?
Short sleeper, I guess, that we were trying to find out, we and other people to try and discover the genes. Obviously one approaches this mainly using mice as your experimental model, and obviously zebrafish as well. We need to find the genes behind this because it's a common feature of people from individual to individual that have different lengths of sleep, just the same as people who've got different IQ and height. But we know very little about the genes that control the length of sleep as opposed to the genes that control the timing of sleep.
Mick, thank you. Priya, we've got someone who's got an answer to the quiz.
Yes, so we have Mark from Bletchley on the line at the moment who believes he has the answer to our quiz.
Hi, Chris. I do believe it's bats.
And you're absolutely right. It is the brown bat that spends 80% of its life asleep. Finally this week, it's Hannah Critchlow with our answer to our question of the week.
This week, we howl at the moon and try to enlighten our minds. Martin Taper wrote in with this.
I've been affected by the moon all my life. I medicate myself to sleep in a full moon, otherwise I don't sleep. I am also affected by air pressure in a similar way. When the air pressure is high, and it's full or near full moon, I'm unable to sleep without medication, and if I do partially sleep, I have wild dreams. When the opposite is the case, I sleep like the dead. Is there a scientific explanation for this?
To answer Martin's sleepless question, we turn to clock doc John O'Neill from the Laboratory of Molecular Biology in Cambridge, where he works on circadian rhythms. But what exactly are circadian rhythms, and how is it relevant to Martin?
Your circadian rhythm is the approximately 24-hour biological clock that ticks away in every cell of your body, priming us for wakefulness in the morning and making us feel sleepy at night.
Aha! So could the moon cycle or atmospheric pressure changes affect our circadian rhythms in some way and disturb sleep? Let's start with atmospheric pressure. What's the data on that?
I'm afraid there is very little that's known about the effects of high atmospheric pressure on human sleep.
Ah, that's disappointing. OK, well, what about the moon? Is there any data linking the lunar cycle to Martin's reports of disturbed sleep and wild dreams?
Now, when it comes to lunar cycles, beyond the historical folklore, the moon very much continues to influence modern-day human cultures, but despite a persistent belief that our mental health and other behaviours are modulated by the phases of the moon, until very recently there has been no solid evidence that human biology is in any way regulated by the lunar cycle. It has been speculated, however, that just like with the circadian clock, which synchronises to the cycle of day and night, there may exist in humans a lunar rhythm that synchronises with the phases of the moon, as has been observed in certain marine organisms. So just last month, Anna Verst-Justice and colleagues performed a retrospective analysis of human sleep data collected under stringently controlled laboratory conditions, with neither the participants nor the investigators being aware of the lunar phase. They found that during the full moon, on average, participants experienced a 30% decrease in deep sleep, otherwise known as NREM sleep, a 20-minute reduction in total sleep, and that it took 5 minutes longer to fall asleep even though they didn't know it was the full moon. This implies that lunar rhythms do exist in humans, and it would seem reasonable to expect that some individuals, such as your listener perhaps, are more sensitive to them.
Thanks, John. So, Martin, you are not alone in your suffering with sleep during the full moon, and scientists are looking to understand exactly why this is happening. Now making a move from the moon to thinking about moving our homes up to a terraformed Mars. Steve Davis wrote in with this.
I frequently wonder where we are heading as a species and see that the one big issue we continue to ignore is a sustainable human population. I have heard the Earth can support about 2 to 3 billion people comfortably and sustainably. Is that true?
So, how many people can Earth really support? And should the 7 billion of us already here be thinking about moving sticks to other areas of the galaxy rather imminently? What do you think about that one?
Hannah Critchlow. And if you can help with our question of the week, please send your answers and speculations to chris@thenakedscientist.com. You can also tweet @nakedscientist. And we have got a forum online on our website, nakedscientist.com/forum. There's a question of the week section where all of these things get debated. That is it for this week. My great thanks to our guests this week, Mick Hastings and Jason Reel, and to Priya Crosby for helping to present the programme. The production was by Kate Lamble. We're back next week, actually, with a show recorded at the Cambridge Science Centre, where we wheeled out 3 scientists and we asked them questions. And then the public took over and we did some exciting experiments too. Join us next week to find out what that was all about. The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust and the EPSRC. My name's Chris Smith. Thank you very much for listening, and goodbye.